Hi, in this video, I'm going to give a sort of conceptual introduction to the Klein-Gordon equation. And I will give a little motivation for why the Klein-Gordon equation looks the way that it does. So the last 100 years of science has taught us that our universe is fundamentally obeys the symmetries of special relativity, but it also obeys the axioms of quantum mechanics. So we've really had to have 100 years of evidence supporting this. So we have special relativity on one hand and quantum mechanics on the other. Now, special relativity, it's very important in really, the axioms of special relativity are a set of symmetry principles. And one of the ways we think about these symmetries is that we need to treat space and time on equal footing. We see that it's better instead to think about time and objects moving, or think about, rather than thinking about just we have this space and objects move through space with time as some parameter, we instead want to work in something known as space-time, where we can really explicitly see symmetries between space and time, where time is acting just like another spatial dimension, or almost like another spatial dimension. It's a little bit different, but almost, right? We're treating them on equal footing. On the other hand, in quantum mechanics, probably one of the first equations that you might have learned in quantum mechanics was the Schrodinger equation, which we can write this equation in different ways, but probably one of the most familiar ones, sorry, that's supposed to be a T on the bottom, looks like this: IH bar d psi dt is equal to minus h bar squared over 2m d2 psi dx squared plus v psi, where v is our potential. So this is the Schrodinger equation. Where psi here is the wave function of our particle. Now, this equation explicitly is non-relativistic. It's explicitly treating space and time differently. We have a single derivative with respect to time, and we have two derivatives with respect to space. And it turns out that the quantum mechanics that you first learn, usually in most physics programs in physics, is really non-relativistic quantum mechanics. Oh, this isn't wanting to let me write the way I want it to write. Non-relativistic quantum mechanics. Okay, I'll just write NR. Right? Non-relativistic quantum mechanics. And so what physicists wanted to do was to develop some new framework which still obeyed the axioms of quantum mechanics and had the symmetries of special relativity. And these early efforts led to what is known as the Klein-Gordon equation. And what we're going to do to write this Klein-Gordon equation is we're going to say, okay, let's consider something where we have the second derivative with respect to space. Maybe we introduce a new equation that also has a second derivative with respect to time, rather than a single time derivative. And if we do that and then we combine things, the Klein-Gordon equation that we end up with can be expressed in this way. It doesn't, you can't see directly getting to this from the Schrodinger equation. That's not, just sort of trying to motivate this equation, where we see, right, whenever you have a Lorentz scalar, which is to say all your Lorentz indices are contracted, there are no free indices, then we know this is something that's going to respect the symmetries of special relativity. So this explicitly respects symmetries of special relativity. And this equation is going to end up providing the foundation for what ends up being quantum field theory, which is the marriage of special relativity and quantum mechanics and is the framework of part that we use for particle physics. And it really comes from, thinking about a Schrodinger equation, trying to create a sort of a new version of a Schrodinger equation that treats space and time on equal footing in the way that this equation does. The thing that I want to note in this class, because we've seen this equation before, although it looked just a little bit different, this is exactly our the equation of motion associated with our phi squared scalar field theory. So this is the equation of motion from the phi squared scalar field theory that we studied. All right, all that we've done is we've traded out, we had some sigma constant that we were keeping when we considered the phi squared model. We just wanted it to be some constant. And now instead we're reinterpreting this constant with where I'm writing an m here, which is it's going to be some mass. All right, so that just sort of motivates briefly this thing known as the Klein-Gordon equation, which again really provides the lead up to what is now known as quantum field theory.